I'm Cliff Trines, Director of General Public Outreach for the National Groundwater Association. It is my privilege to introduce our two presenters. Dr. William M. Alley is Director of Science and Technology for the National Groundwater Association. Before serving in his current capacity, Mr. Alley was for nearly 2 decades Chief of the Office of Groundwater for the U.S. Geological Survey. He also served as the Groundwater Coordinator in the National Water Quality Assessment Program and Coordinator of the Regional Aquifer System Analysis Program. Charles Jobe is the National Groundwater Association's Regulatory Affairs Manager. Prior to serving in his current capacity, he was Chief of the Infrastructure Branch in the Drinking Water Protection Division of the U.S. Environmental Protection Agency's Office of Groundwater and Drinking Water. During the presentation, feel free to type questions in the question box and hit send. At the conclusion of their presentations, Bill and Chuck will answer your questions. So without further delay, I'll turn it over to you, Bill.
Hey, thanks, Cliff. And welcome to Protect Your Groundwater Day, everybody. So I'm going to give the first part of the presentation, and as Cliff mentioned, Bill will give the second part. So the title of my presentation is, as you can see there, Groundwater Sustainability Concepts and Myths. So, just a quick note on the global importance of groundwater. I think most people are aware of these facts, but they're actually rather important in terms of just how important groundwater is in terms of drinking water and food production, as well as just general economic and ecosystem issues. Just here in the United States, about 70% of groundwater used is for withdrawn irrigation, which is by far and large the largest user, and about 23% of groundwater extraction is used for domestic uses, public supply. So my outline is quite simple. First, I'm going to talk a little bit about groundwater sustainability. Then I'm going to talk about human versus hydrologic timescales, which present real challenges in terms, and cover a few groundwater myths. So NGWA has adopted essentially the definition of groundwater sustainability used by the Geological Survey in Circular 1186, which is probably many people have seen, the development and use of groundwater resources, current and future beneficial uses without causing unacceptable environmental or socioeconomic consequences. Some people prefer actually a more quantitative approach to it, but the fact is that groundwater sustainability is really more of a perspective to frame scientific knowledge, not a scientific concept in itself. It's essentially, as defined before, the end result of public acceptance of the trade-offs of development. And as groundwater hydrologists, we provide information on the long-term consequences of groundwater pumping and help, ideally, in helping make the societal decisions. I think an interesting way to look at sustainability is this graph here from the Upper San Pedro Partnership in Arizona. So essentially, this is a storage change versus time. You have start out with a steady state during pre-development, and then gradually you're depleting the groundwater storage till at some point in time there's concern raised. And at that point, really your options for sustainability there are shown kind of bounded. You could cease pumping and there would be some gradual replenishment of groundwater storage. Could be quite a while in this particular, in the Upper San Pedro. Or you might choose to just achieve some new steady state with recognizing it as a large part of the resource, and a whole range of options that would fall in the category of sustainable use there between those two endpoints. I think the other key aspect is really to distinguish the fact that water from pumping comes from both capture and storage, and initially for a given well, this is a well near a stream, you would have water, all of it would be coming from storage, but it gradually, over time, if you reach a new steady state, that is, it's all coming from capture. And what's interesting, and these are old data, but they make the point. What these pie charts show is for a number of the RASA studies that USGS did back in the day, the percentage of the water that's coming from decreased storage modeling studies is shown with red, and the percent from increased recharge is blue, and yellow is decreased discharge. Now, increased recharge versus decreased discharge can depend on how you frame your model, but the key point is that the storage depletion is not as much as many people would expect. And of course, a couple of those systems, like the Floridan and the Edwards Trinity, were treated as steady-state systems, so there's no storage depletion and no simulations. The other interesting thing here is if you look at the western aquifers, the Eastern Snake Plain and the California Central Valley, those hatched areas indicate infiltration of irrigation water. So there's huge change in essentially the hydrologic cycle in these major irrigation areas. So the point is that capture of oftentimes the stream flow is the major issue associated with. The other key point is that one needs to consider management practices, all of which can have huge impacts on really what your sustainability is. So sustainability can be defined differently depending on one's use of recycled water, managed aquifer recharge, and how you use groundwater and surface water conjunctively. A good example of that, recently published by Bridget Scanlon and others, is these graphs show for Arizona, the AMAs in the top graph are areas where active management areas where Arizona, through its legislation in 1980, essentially and recharging and also regulating groundwater use. As you know, we've been in a drought period over the past couple of years, a decade or more actually, in the Southwest. What's interesting there is for those various AMAs, you can see that the groundwater anomaly, measured as some sort of average of groundwater changes, it's actually improved, if you will, over time and reached some kind of balance. Whereas if you step outside of those active management areas, you essentially have surface water from the Central Arizona Project that's supplementing the groundwater, and you have these regulations in place. But in these other areas, not so lucky, outside the AMAs, you can see what's happened to the groundwater levels. They've dropped quite a bit in those areas. So here, and this is a good example of a case where really the management practices are having a very large effect on the sustainability of the system. Okay, so turning to our second topic here is really the difference between how we think about time as humans and hydrologic time scales. So the top there shows human time scales, and the bottom hydrologic with the circles showing sort of average residence time. Now, the groundwater's average residence time is somewhat over 1,000 years if you look across the world, but of course that varies from days to a million years or longer. So it's a very wide range. The point is it's very long in most cases relative to either government terms or how we think our groundwater policy horizons, which are tending to get longer, or even multiple generations. That creates quite a challenge for us in terms of what sustainability means. And these vary tremendously amongst different aquifers. The Edwards aquifer is a fast-responding aquifer. It even has an index well that people keep track of, shown there. It's kind of almost like a surface water reservoir underground in a sense, and being able to use that index well to look at water levels in the aquifer. On the other hand, if you go to the Colorado Plateau, it's a nice modeling example from Stan Leek and others with the USGS. There was a development planned for LUP in Arizona on the Colorado Plateau. And the question was, what would those effects be on those two creeks, Steer Creek and Chevelon Creek, lower right in that map. And the simulation went for 50 years, from 2010 to a little past 2060. And then they stopped withdrawals in the model. And it's a nice example to sort of illustrate to people, first of all, three things, I think, really. First of all, they were pumping in this simulation about 9 CFS, cubic feet per second. And you can see the stream flow capture is much less than that because it's being spread out over time. So that's somewhat good news. The other issue is, of course, it comes from not just the nearest creek, but both of those creeks are contributing to stream flow capture there. And finally, at least according to the simulation, when you turn off the pumps at 2060, there's a couple decades until you actually have the maximum impact capture take place. So I think it's a nice example of sort of how, particularly for some systems, you can have these very long time frames between when you do make changes to the pumping scheme and when you actually see the effects. But it's not just stream flow depletion. Land subsidence can have the same effect. This is Antelope Valley in California. Two pictures are taken not too far from one another. One is at Edwards Air Force Base in the lower right, which you can see the fissure from land subsidence. There was something like 150 feet of drawdown and 4 feet of land subsidence at that area. Even forced closure of the Space Shuttle's alternate runway at one point at Edwards Air Force Base. The blue in the graph shows the depth to water in feet below land surface, and the purple shows aquifer system compaction. And these are essentially from 7 years of paired water level and aquifer system compaction measurements done by Michelle Sneed and Evan Galloway. And what's interesting there is you can see that the changes in water levels, very strong seasonal component to it. And you can see that the compaction really isn't paying much attention to those. You can see little wiggles in the purple line, but essentially it's a continuing decline. And the reason for that is that area has had these large water level declines and has very thick aquitards which have slowly draining over time. So you have this delayed drainage and delayed compaction in the system. And so you can't just stop pumping and the land subsidence problems go away when you have these thick aquitard systems. Okay, final example. It's not just, it also affects water quality. So this is an example from the Chesapeake Bay where there's a lot of attention placed on nutrients in the bay. And basically putting in place best management practices on farmers to reduce loads of nutrients to groundwater and to surface water. So they're being asked, a lot of people are being asked to take these measures. But the problem is about half of the nitrate in the bay comes from groundwater discharge, and so there's a strong delay in the system. This is a simulation study done by Ward Sanford, and the pie diagram essentially shows the base flow age distribution in the Chesapeake Bay. This is on the Delmarva Peninsula, actually part of the Chesapeake Bay. And the graph shows the nitrate load to the bay with the dashed line there around 5,000 metric tons. That's the current total TMDL target for nitrogen load to the bay. And what you can see is under 0%, it just keeps growing, load reduction. Even with 13% load reduction put in place in maybe 2012 or so, you can actually bring it to somewhat of a steady state for a couple decades. But it really takes a 40% reduction, and this is just in calculating the load to the water table, essentially. And by 2050, you start to approach the TMDL target. So this presents a challenge in terms of convincing farmers in the Chesapeake Bay region that they should be doing best management practices when these effects are felt out in time. Okay, so if we turn to the third myth, one of which I think most people are very aware of now, but is that natural recharge equals sustainable yield. That's a myth. And a good example of how to explain that is shown here with this surface water analogy. You have a dam, and you have a no pumping situation, then and with some downstream releases, and then if you withdraw water equal to the outflow, but stop the outflow, then you maintain some steady state condition in the reservoir. But the problem is taken care of, you've wiped out the outflow from the system, which of course in a groundwater system is important. So that's why you still see this all the time where the recharge is used as a some sort of statement about the sustainable yield of the system, and it's just not true. Now, having said that, I think there's also kind of a it propagated maybe another myth, and that is that recharge isn't important. And of course, recharge is very important. Any system's got more recharge, it's likely to be able to have more development associated with it or more water available. It's obviously important for calibrating models, and it's very important for any water quality issues. So it's just not the parameter to use in terms of describing the sustainable use of a groundwater system. Wiped out that myth. So the other one, which seems to be quite popular today, is that we need to know the groundwater storage volume. It really matters. And so, of course, obviously, it's the recoverable groundwater storage we have. So if you take a system and multiply it by its specific yield, you can come up with some kind of estimate of the volume of recoverable groundwater. But even that's not particularly a good number to have, not particularly important. And that is because you can have a very small part of the total volume in groundwater storage can have very large effects on surface water quality sites, and these often become the limiting factors to development. Show a few examples there. The Houston area, center top, has a vast groundwater resource, but because they have land subsidence that's causing flooding problems, being on the coast, they've essentially done it's still in the works, I think, moving to partial reliance on surface water, large-scale reliance on surface water, actually, because the pumping is just causing land subsidence problems for them. The Upper San Pedro on the left, I already mentioned, that shows the town of Sierra Vista there. They've depleted maybe 1 to 2% of their total volume of groundwater in storage in the Sierra Vista subwatershed there, and have been undergoing tremendous amounts of discussions and trying to cut back on water use. A small dip into their volume because of concerns about effects on the riparian system of the Upper San. Edwards Aquifer, which we showed before, just a few meters of change in groundwater levels and groundwater storage can affect spring discharge, which is required for endangered species habitat. And finally, the Republican River Basin, which sits in the High Plains Aquifer region of Colorado, Kansas, and Nebraska, has been the focus of a number of battles back and forth in Supreme Court decisions after only a of about 3 to 5% of the volume in storage affecting base flow, cutting it in half. So those are really the driving factors, not the volume of groundwater in storage. And, the reason for the stream is quite easy to portray here. When you look at a groundwater system in a partially penetrating stream, you can see that a very small change in the volume of the groundwater system is going to have a big impact on that stream. So key information, as opposed to total storage, is if you're looking at surface water groundwater systems, or gradients and saturated thickness, land subsidence, water levels, water quality flow systems, and pumping costs, the depth of water. So those are much more critical issues oftentimes than the total volume. So we've taken that one out. The third one is the tendency to think of groundwater as drought-proof. In other words, it's going to be there when the drought comes, and we'll be able to use it. Which may be true in some cases, but not in others. And associated with that concept is this concept of resilience. This happens to be the definition that we've adopted within the National Groundwater Association for resilience, which can be either the ability to withstand either a short-term shocks to the system or longer-term change. There's a couple key sub-concepts there that one needs to define a time frame, applies to both water quantity and quality, and it's an important part of groundwater sustainability often. So how resilient is groundwater? Well, not always. This is a show of the Central Valley change in groundwater storage over time from 1962 to 2012-14. And you can see by the red line there that there's ups and downs. The green in the background shows the surface water deliveries, which increase during wet periods and decrease during dry periods. But there's a steady overall decline in groundwater storage, which has led to, in particular, subsidence problems that have become renewed over the past few years in much of the Central Valley, actually. So I think the story there is that we need to build more explicit recognition of climate variability and even run climate variabilities and models and project groundwater conditions over years to decades to look at what really happens when we hit these drier periods. I think the second is the importance of raising awareness about maintaining groundwater as a reserve. So monitoring water use and water levels are key components of that. Also, I think it points to managed aquifer recharge as a critical component, and we saw how important that can be, useful that can be in the Arizona example earlier. And ideally, we're kind of stuck with the laws we have, but work toward laws, regulations, and incentives that actually encourage use of surface water during wet periods and prepare. I think that's the operative word for increased groundwater use during droughts. So, and again, data are key to trying to understand both sustainability and resilience. And this is sort of a statement that we've gotten from a number of our members about the importance of federal funding for cooperative groundwater quantity data collection and other types of data collection, such as water quality, aquifer mapping, and so forth. And then we've also, of course, been big proponents of this National Groundwater Monitoring Network in NGWA. So at the final slide, before we turn it over to Chuck, is just really to deal with all these issues of groundwater sustainability and drought-proofing groundwater, et cetera. Is in the ideal, one has an integrated modeling and monitoring system that works somewhat as shown there, where you have maybe long-term monitoring networks that are in place to measure water levels and water quality, stream flow, and other components, an important one being water use, actually. And then periodically over time, you revise your conceptual model, and that feeds into your simulation model of the system. And meanwhile, there are other types of information that are contributing to that effort. And then ideally, and this step rarely takes place, these two, is once you've finished that particular phase of the modeling, you actually feed what you've learned back into the monitoring network and adjust the network appropriately to better feed into this integrated modeling and monitoring and modeling scheme. So with that, and before we take questions, I think we'll turn it over to Chuck, who will continue with NGWA Best Suggested Practices for Sustainability.
Good afternoon, this is Chuck Job. Thank you very much, Bill. And we certainly want to build on Bill's presentation to focus on groundwater sustainability, but from the perspective here in the second part of the presentation on the National Groundwater Association's best practice principles. There are a number of reasons to focus on groundwater sustainability. Bill covered some of them certainly, and we wanted to highlight a few more. Certainly surface waters are allocated, fully used, with the demand for groundwater increasing. 2010 irrigation use from groundwater is 148% greater than it was in 1950. Groundwater use along coasts continues with the result of saltwater intrusion. As you can see from the map there on the right, the locations of major saltwater intrusion along the Atlantic coast there, as an example. The 16-year drought across the western United States that Bill referred to. The demand for water in energy production continues. And with that, the oil and gas industry produce brines that need to be disposed. And of course, population growth increases demands for drinking water and food production. And just as a further point of emphasis on the drought aspects of why we're focused on sustainability, drought is not just an issue in the West, obviously, it's an issue across the country, as this slide shows. The United Nations has taken a focus on the water sector, as you all are aware, and certainly they focused on the safe, reliable water supply, as you can see here from these targets. And building on that and building on the work that Bill outlined and much other work, the association, the National Groundwater Association, put together principles to guide best practices for groundwater resource sustainability early in 2016. So my outline is basically the outline that these principles provide for the rest of my presentation here. So I want to just cover these 8 and then we'll provide a little deeper perspective on each one of them. First one, collaborate with adjacent local and regional jurisdictions within and among states and nations. 2, set groundwater resource objectives and forecast water demand. 3, incorporate the hydrologic cycle and natural processes in groundwater management. 4, minimize the carbon footprint of groundwater infrastructure and production. 5, implement source water protection or remediation for private and public groundwater uses. 6, measure, report, and share resource status data with residents and other jurisdictions. 7, prepare to avoid disruption from extreme events affecting reliable, safe groundwater supply. And 8, reassess groundwater management on regular intervals. So taking a deeper look at each one of these principles, the first one, to collaborate locally. Certainly it recognizes groundwater flows under jurisdictional boundaries. It's important to have a common understanding of the resource because of that nature of groundwater to flow, and conduct local groundwater resource audits, develop a groundwater budget, a water budget, including groundwater, and share plans, objectives, and data. Number 2, in setting groundwater resource objectives, we want to focus on publicly vetted but want to also consider rules, codes, and laws that can reflect those objectives in the management of aquifers and groundwater, and evaluate future water uses and their alternatives. 3, incorporate the hydrologic cycle. Here we want to focus on storing water underground to reduce evaporative loss and protect groundwater quality. Facilitating recharge by use of green infrastructure and native vegetation. Avoiding land subsidence, which Bill had focused on. Preserve groundwater for ecosystem diversity. In minimizing the carbon footprint of groundwater infrastructure and production, we want to evaluate alternatives for minimizing life cycle footprint and costs. Use most efficient equipment, reduce water loss in storage and delivery, and promote conservation and reuse of water as an alternative source for the future. In implementing source water protection and remediation, you focus on eliminating and reducing sources of contamination, protecting usable groundwater from future contamination through practices and laws, and remediating contaminated groundwater. In measuring, reporting, and sharing resource status data, we want to focus on monitoring water levels, quality, and use, and then report those results, hopefully to show achievement of groundwater resource objectives. 7, preparing to avoid disruption from extreme events affecting reliable, safe groundwater supply. We'd want to consider the effects of extreme weather events and human interventions. We want to address water supply vulnerabilities of the infrastructure and operations, and establish processes for timely recovery from disruption. And 8, reassess groundwater management on regular intervals, indicating here evaluating the availability, source, protection, provision, use, and resilience alternatives, conducting life cycle assessments of both the natural and constructed infrastructure, and then adjusting codes and laws and practices for cost-effective provision of safe, sustainable water. The National Groundwater Association offers assistance to communities, businesses, and governments to achieve water sustainability by identifying local resources within its membership to assist in developing plans and implementing best practices, using these principles to provide safe, sustainable groundwater resources and support your community's health and natural and economic vitality. We look forward to working with you on needed services to provide safe, reliable groundwater. And at this point, we would like to entertain any questions you may have. And you can provide us your questions by clicking on question on the box there, and then typing your question in the box, and then click send to send it to us. So please provide those questions, and I'm going to turn this over now to Cliff Triance.
I want to remind people about being able to type their questions in the question box, and I also want to let you know that the 2 PowerPoint presentations are available as handouts. You may see there on your little control panels a place to click on handout. You can download those, and we will also be sending a recording of this webinar, a link to you after the webinar. So we'll go ahead and start with some questions. We have a question here, Bill, for you. Can you elaborate on how stakeholder participation plays into sustainable development of groundwater resources?
Sure. You know, groundwater is a shared local resource, often with many users. And so there's the idea that the management decision should have, people have a fundamental right to be involved in the decision-making process. So, and there's a lot of sectors that need to be represented, from those interest from agriculture to water supply to the environment. I think that by engaging the community, it can be a driving force for fostering trust, acceptance, and support for management actions and costs, and ultimately compliance. And I think that's shown worldwide, where just the top-down approach just doesn't work. Unfortunately, takes a long time oftentimes for this community engagement, but it's an ongoing and should be an ongoing and never-ending process as part of resource sustainability.
The next question I think is somewhat related, but the question is, what are some of the impediments to wider adoption of managed aquifer recharge? Is that related to what you just said, or is it bigger than that?
Yeah, so managed aquifer, some of it is education, so people's awareness of it. I think some of the major impediments have been a lack of certainty around the rights and entitlements, either to source waters or, importantly, to water recovery. And certain states, again, Arizona is a good example of putting out a lot of regulations to try to make sure if you store water underground, you're going to be able to get it back. I think there's a lot more information needed on the cost of the life cycle costs of managed aquifer recharge relative to other options. So people kind of shy away from that. And I think requires a stepwise approach, again, in stakeholder involvement from the beginning, so you get people aware of both the strengths and limitations and hopefully on board with the concepts and get their input. In addition to those, I think from a technical point of view, lots of times the key technical issues are water quality issues, either making sure that you're not going to release arsenic or other trace elements in the subsurface by changing the water quality, or and so a lot of the issues that have to be resolved with, and sometimes that can be done more with pilot type studies, is to make sure you're not going to have water quality issues associated with any managed aquifer recharge system.
Just kind of a follow-up on that question. Can you break down different approaches to managed aquifer recharge, and what seems to be are there any trends in that?
Well, the most common approaches are basin spreading or well injection. I think basin spreading, I don't have statistics on this, but I think basin spreading seems to be a little more, it's more widely used. Certainly there's some very large basin spreading operations in states like Arizona and California, where you don't have the land or the right geology or soils. Well injection is also used, and again, there's a lot of systems along the coast of California, and also on the East Coast that deal with that. So those are the principles. There are also in some areas of this area in Southwest, people use Veda zone wells, which are essentially wells that don't make it all the way down to the water table, but water is injected into these and then percolates down, and a number of those exist and seem to be used. Not quite as popular as the basin spreading and the well injection. And the well injection can come in the form of either a single well that pumps and extracts, or it can be one well injection and another well or wells that are used for extraction.
Thanks, Bill. I have a question for you, Chuck. How can I get a water budget for my community?
Well, typically, I would say that it would be best to contact the local water agency, the water department, or perhaps local county sanitarian. Another approach would be to contact a state water agency who may have actually provided a permit or permits for groundwater wells in the area. They often do models to determine that there is sufficient water for additional wells. So they would be able to at least get you started on this process. And I think that it's those sort of key points of contact locally that where water is clearly in their purview, and that quantity and quality are of concern, that they would be most likely to have information you could use. Certainly talking to local universities or colleges that have a program that deals with water. Many of the departments now do have water programs at colleges and universities. Would be an excellent source of attempting to put together a budget. And Bill may have another perspective on this. I'd really like to offer him the opportunity to respond too.
I think you kind of covered the question, Chuck.
Okay. Thank you.
Well, here's one either or both of you can answer. What are the groundwater sustainability principles that need more emphasis or should be higher priority? So I guess they're trying to get a sense of priority as far as the principles that need to be employed.
I'll be glad to take a first step toward answering that. I would say that of all of the 8, there's probably a couple that people typically may not think of as much. The first one that I would suggest is setting groundwater resource objectives. That was the second one. It takes a lot of discussion, a lot of collaboration to figure out how a community wants to best use its groundwater. So setting those resource objectives and then coming up with a forecast for water demand based on those objectives is an important step. But the measuring and reporting and sharing resource data, I think probably measurement is not as centrally focused on locally and except in places like the Edwards Aquifer, where there's a state mandated process to go through to measure aquifer levels, groundwater levels, and use. So I think that was the second one. And I think the third one that I would say is reassessing groundwater management on a regular basis. That often is not thought of. It's usually sort of in a crisis mode, and if communities could get more on the path of doing that on a regular basis, it would probably help them with some of the other steps that clearly would help the community have a safe, reliable water supply. Bill, any other perspective on that?
Sure. Yeah. So I think those are actually excellent points. I guess a couple things I would emphasize in addition is a little bit of what you're adding to a little bit to what you said, Chuck, is the importance of getting involved in data collection early rather than later, because you can't make up for it. And ideally you want to have a baseline data before you even actually impact groundwater systems, but sooner the better there. And the second thing I think is sort of the educational component and the stakeholder participation initiatives, again, because that takes so long to work through those aspects, the sooner the better in terms of trying to engage the public, both through an education and from a stakeholder point of view.
Thanks, Bill. Here's a question to you as well. It's kind of related. What are the critical data needs to support sustainable groundwater development?
Okay, so I mentioned a little bit of that at the end in terms of trying to have kind of a systems approach to looking at groundwater systems. And I think one thing that really is important is to keep in mind that these are three-dimensional systems. So it's not just a matter of laying out something over a two-dimensional framework. And so thinking about them as three-dimensional systems and developing a 3D conceptual model, I think are very important steps. And what we see typically is that there's no magic bullet approach to water level monitoring, or that's not going to do it all for you. It's a combination of water use estimation, water level monitoring, remote sensing applications as part of INSAR or for land subsidence, or as part of estimating water use from Landsat data, or even the GRACE satellites providing a unique measure of groundwater storage changes. So I think that the key is to think of them as groundwater 3D systems, continually be reevaluating your monitoring programs, and getting started early, and having multiple types of data that you can look at in terms of your groundwater systems are all important features there.
All right, thank you. Have a question. What does it mean to incorporate the hydrologic cycle in groundwater management? Either one of you.
I'd be glad to start it off. This is Chuck. I think that we don't want to just look at in developing resource objectives, look at what we have and then what we're going to use and project from there. But we want to make sure that we're looking at the whole hydrologic cycle, the precipitation, historical, certainly recent events, precipitation, and also any other major planned uses that perhaps maybe don't exist today, but perhaps could exist or are planned to exist in say, state planning or local planning, county planning, that would impact discharges. So I was really thinking about the whole cycle, how we manage stormwater locally, and how that will enable any of the recharge that Bill is talking about, any of the other key factors that would influence water use. But it's really looking at the whole hydrologic cycle and sort of placing the different aspects of its management in that context, as opposed to just looking at what we have, what's available today, and what the uses are in the future. Bill probably has a perspective he'd like to share on this too.
Yeah, similar. I would say if somebody says, what's the hydrologic cycle, how's that relate to sustainability? I would say, you know, with few exceptions of maybe some really isolated non-renewable aquifers out there, all these groundwater systems are connected to, as you mentioned, to the surface water, to the precipitation, and so forth. So it's and they're dynamic systems typically. So to me, that's what it means. You think of the groundwater system not as just like an underground lake, but more as a dynamically connected system to the environment, is how I think of incorporating the hydrologic cycle.
Okay, thank you. Chuck, I think you mentioned about how NGWA members could work with communities, businesses, and governments. Can you explain how that would take place?
Yes. At sort of a high level, I think that communities, if they have issues with water supply, they're supplied by groundwater now, either fully using groundwater or perhaps groundwater is a portion of their supply. Either way, they have issues with how to plan, how to deal with issues that have come up. They can certainly contact the National Groundwater Association. We have an 800 number, and you can see it on this slide. And you either contact Bill or me. You can see our extensions there, or talk with the operator and let them know, let us know what your concern and problem is. The association has 11,000 members, over 11,000 members that are drillers, equipment manufacturers, and groundwater scientists and engineers. Somewhere in that spectrum, we probably have someone who has worked on issues like those issues that you might have in your communities. So we will look very much forward to helping you work through what that issue is, and then we can work with you on how best to provide services that we could offer, certainly at cost, but offer and collaborate with you and identify other aspects of the issue and other people that might want to be brought in. And we've got committees that focus on very specific topics within groundwater. So we've just got a very broad, extensive, and deep set of capabilities within the membership.
A question for you, Bill. The question is, what groundwater monitoring and reporting needs to occur? I think some of that's been addressed, but I'm wondering about the reporting part, and you mentioned also the National Groundwater Monitoring Network.
Right.
Yeah, what really needs to be measured and reported, and so that all water resource managers can benefit from this?
Okay, so I guess I would say in the ideal, all information about groundwater that's collected would be available to most anybody, either consulting firms or the general public or state agencies and so forth. So trying to make the data accessible, and we have lots of more opportunity to do that today than we used to with computer systems. The National Groundwater Monitoring Network is a specific activity that is attempting to make it so that people, if you want to have water level data and some other basic types of information available for a particular area, it may cross state boundaries, for example, and may be housed in multiple agencies. We're not trying to create a master system that has all the data, because that would be a nightmare to manage and to deal with changes and so forth, but that you could actually have access to find out what's out there and have access to it, and then have some confidence that it meets basic standards. So I guess that's the other aspect of it, which is that, you know, the importance of documenting the approaches used to collect any kind of groundwater data and undergoing appropriate levels of quality assurance, et cetera, to make sure that information's sound and meets certain requirements.
Excuse me, what can you say about the timeline for development of the National Groundwater Monitoring Network?
Well, it's taken a while. So that idea has been out there for, I don't know, I lost track, but it may be 10 years, I'm guessing. And so it's just starting. It's been implemented through funding through the U.S. Geological Survey, actually. So I think it's on its maybe second year of funding. If somebody could correct me on that, but it takes a while. One of the problems we have, maybe this is an educational aspect, is that it's hard to convince people just how important groundwater data is. Again, because it's an unseen resource and it's not typically a flooding, causing flooding or anything that's noticeable that tends to get people to act. So it's kind of quietly changing, and so it's a challenge actually to get the appropriate level of monitoring in place, and then also to keep the funding coming. I think, again, that's something which NGWA tries to work on in general, is just trying to support the idea of the importance of groundwater monitoring of all types.
Okay, we're down to our last question, unless somebody sends one in quickly. Well, there's a question about what extreme weather events are related to groundwater, and how can a community avoid disruption for them? I think some of that's been addressed, but I guess I'm wondering, maybe I'd add on to that. We have extreme weather events, but there's also, as we know, been a lot of discussion about global climate change. How has the picture in terms of forecasting what's going to be happening here with groundwater changed because of this discussion about global climate change? And just if somebody wanted to think more deeply about how to plan for a sustainable groundwater, how do you consider global climate change?
Yeah, that's a hard one to do quantitatively, but so for example, I think the answer is a definite yes in terms of places like the Mountain West, the Rockies, as well as the Sierra Nevada, in terms of having a lot, essentially less precipitation falling as snow, and runoff happening earlier in the season creates a whole different sets of management strategies that one has to think about, both in terms of operating reservoirs as well as the stress and strain, if you will, on the groundwater resources of that region. So I guess the answer is it depends on sort of what the projected, what your climate conditions are today that are driving things like groundwater pumping and groundwater recharge, et cetera, and how those might be impacted by climate change. And it's easier to deal with the temperature effects. The precipitation effects are still kind of debated in many places, but it's something which people are thinking about and trying to essentially adds to the uncertainty level, if you will, that they have to build into their plans.
I would also say that if people are really focused on this and want to know what is happening locally, that they certainly could contact their local agencies that deal with weather emergencies and understand who they work with relative to data that they're using to project their needs. And also, they could certainly get in touch with state planning agencies, state water planning agencies that are focusing on this very intensively, as we know, and interacting with other organizations. There's a high level of focus on this relative to infrastructure, relative to agriculture, and a number of other key resource objectives. So there's a number of places to go for information and input.
Well, thank you, Bill Alley and Chuck Jobe, for excellent presentations. And as Bill mentioned, today is Protect Your Groundwater Day, and this is an attempt to try to bring more visibility to this unseen resource that Bill referred to. And I know some of you are involved in promoting Protect Your Groundwater Day and groundwater protection, and we focus mostly on protection against contamination and also in terms of wise use of the resource, which is very relevant to what we're talking about today. So I want to thank you for that. We also would ask that you put on your calendar National Groundwater Awareness Week, which is another event devoted to trying to draw public attention to this most critical resource of groundwater. And for your information, write down these dates, March 5th through the 11th, 2017. That's March 5th through 11th will be the next National Groundwater Awareness Week. So thank you, everyone, for participating. Look, grab those handouts if you want to download them now, and I will be sending you a link to the recording of this webinar. So with that, I wish everyone a good afternoon. Thank you.